Okay, in this video we want to do a few more examples on optimization. So a farmer has 200 feet of fencing, wants to fence off a rectangular field that borders a straight river. So he needs no fence along the river. What are the dimensions of the field that has the largest area? So let me start by making a picture. Draw the river in here. And we're fencing this way along the river. So we could say that this is X, and this is Y, something like that. Okay. So I guess my first thing, I want to figure out the largest area. So in terms of my variables, I'm going to write an area equation. It's X multiplied by Y. And what we talked about, remember, make some note. This is the equation we want to play with. This is the important one. When we take the derivative, we're going to take the derivative of area because that's what we're trying to optimize. Okay, next we need a constraint equation. So what we know here is that we have 2,400 feet of fencing, so that 2x plus y must be equal to 2,400. Well, that means that y is equal to 2,400 minus 2x. So now I can substitute that in for y. I can rewrite my area equation as x multiplied by 2,400 minus 2x. And I guess, we could keep going and say, well, it's 2,400x minus 2x squared. Now, next we maybe should make some note of the domain. Maybe I'll just kind of put that off to the side here. Remember, domain is important when we're thinking about doing absolute maximums and minimums. It's possible for those to be at endpoints. So it's good to look at those and see if they're viable options. It's also good to just look and say, are solutions realistic, the ones we find based on the domain? Well, here, x, of course, has to be greater than 0. It can't be 0. And looking at what y is equal to, I usually think is the best way to get the top bound. It has to be less than 1,200, or we wouldn't have any material left for y. We could plug that in and say if x were 1,200, y would be 0. And that can't happen. So what I see here are that my endpoints are not options. It can't be 0 and 1,200. So I am looking for critical points, not endpoints. So the derivative, dA dx, is equal to 2,400 minus 4x. Set that equal to 0. I think we can do that in our head. So x is equal to 600. We go back to figure out what y is. We just go back to what y was equal to in our constraint, and we can solve, and we can get 1,200. And those are the dimensions that solves the question. All right, next, what are the dimensions of a soup can of the greatest volume that can be made with 50 square inches of tin? And what is the volume? Okay, so, I made a little picture here. We could certainly say, here's the radius, here's the height, like that. Volume of a cylinder is pi r squared multiplied by h. Any kind of prism shape is the area of the base multiplied by the height. And again, this is the equation we're going to be playing with. Okay, we got to make some kind of note. That's what I want to find the derivative of. I should be searching for dv, d something, depending on what variable I eliminate. Now, the 50 in the problem, the 50 square inches, this represents the surface area. Okay, so we need, as we construct a constraint equation over here, I'm going to say that that's equal to, well, I have two circles to make the top and the bottom of my can, so 2 pi r squared, okay, two circles, and the lateral area, what we would consider the part that aren't the two circles, is actually a rectangle. If you unfolded it or uncurled it, with a base equal to the circumference and then of course the height is just h. So now you think about the algebra that would take place here. We'd subtract 2 pi r squared. I should mention here, a lot of times it doesn't matter what variable you solve for, but in this case I absolutely think it does. We want to solve for h because there's only one h that appears in our constraint equation. It'll be easier to solve for. So 50 minus 2 pi r squared over 2 pi r. So now we can substitute for h. So volume becomes pi r squared multiplied by 50 minus 2 pi r squared over 2 pi r. Now this looks ugly. Let's do a little simplifying. Pi divided by pi is 1. R squared divided by r is just r. And then you take a look inside these parentheses. All that's left on the denominator is a 2. So 50 divided by 2 is 25. 2 pi r squared divided by 2 is just pi r squared. So I can write this as r. I'll leave that out for a moment. 25 minus pi r squared. Now multiply the r in. 25r minus pi r cubed. Okay, so here's our equation. Came out pretty darn nice. In the interest of time, I'm not going to talk about domain on this one. Needless to say, maybe that r has to be greater than 0. We could certainly solve using this. We could solve for what h has to be, or what r has to be less than. But let me just move on to dv dr. Okay, we got the derivative is 25 minus 3 pi r squared. We set that equal to 0. So 25 is equal to 3 pi r squared. So 25 over 3 pi is equal to r squared, square root, like this. Okay, let me do a little simplifying then. R is equal to 5 over the square root of 3 pi. Again, in the interest of time, I'm going to stop. The actual question was, what is the volume? You'd substitute this back in here to get what the volume is. Okay, but that is the radius that would maximize the volume with a set surface area. Okay, in this last video, I'm going to show you one that actually is a pretty easy problem, but kind of a rough setup. Find the largest rectangle that can be inscribed on a semicircle with radius 5. First of all, I just want you to remember that how we graph a circle from pre-calc is we do x squared plus y squared equals 25. Okay, x squared plus y squared is equal to the radius squared. When we wanted to graph that, we started by trying to solve for y, so we would do something like this, and then we would square root. By rights, algebraically, I should have a plus or minus out front, but since I'm only graphing a semicircle, I'm going to stop here. This is what I graphed to get that shape above. Okay. Now, let me draw my picture. I'm inscribing a rectangle in here, like this. What I like to do when I put a rectangle or any shape in is I like to just mark up and say, okay, right here, I'm going to name this point x, y. So this point over here would be negative x, y. And a lot of times that helps me just think about the area, because the base of my rectangle, just one side of this is x, and of course this other side is also x, so the total base is 2x. And the height, easy enough, that's just y. So the area is 2xy. Now what seems tricky here is it seems like you don't have any relationship to get rid of one of the variables, but in fact you do. We know what y is equal to. So like I said, a lot of work setting it up, but now you just replace with what the equation is. It's actually pretty nice and easy. Now, there are lots of ways you could do this derivative. You could certainly use the product rule. I want to show you one other way we could do it. Okay, I'm going to make I'm going to rewrite 2x as the square root of 4x squared. And if you look at that and think, well, why? Why would you do that? Things that are both under a square root can be multiplied together. So I can actually multiply these in, and it becomes just the square root of 100x squared minus 4x to the fourth, which, knowing I'm going to need the derivative, I'm going to write this as 100x squared minus 4x to the fourth to the 1/2 power. Okay, let's do the derivative. dA dx, 1/2 out front, leave the inside alone. Now it's to the negative 1/2, multiplied by the derivative of the inside. That. Maybe rewrite this a little bit. Could even go a little further. Okay. And of course, we want to know when this is 0. Well, the thing about it is, I don't really care when the denominator is 0, because I don't need this thing to be undefined. I need it to be 0. So really, all I need to focus on is when is this equal to 0. Could factor an x out. Oh, I lost that. It should be cubed. Okay. So one of the answers is 0. One of the answers, so 0. And this one, if you solved it, 100 minus 8x squared equals 0. You get plus or minus the square root of 25 over 2. Or, of course, just 5 over the square root of 2. Well, 0 isn't going to be our answer. We can't place x at 0 and get an answer, so that's out. The plus or minus thing, well, remember, we wanted 1 plus and 1 minus. So the x is going to be 5 over the square root of 2. To get the area, you know what, I can rely on you. You could plug that back in here and get that answer. I'm going to stop right there.